You got it? Okay, let's begin. Dear Heavenly Father, we thank you for this day. At the end, thank you for these students. Thank you for the weekend just completed. Help us to just make the most of this time we have together to study your creation, Lord, to learn more about math, Lord. In your name I pray. Amen. All right, so let's see here. I think I owe you a definition. If V is a real inner product space, as usual, over R, of course, right? What else would I mean? Then we say T, let's say L, a linear transformation from V to V, is an isometry. And, well, we could be more specific here. In fact, it's an orthogonal transformation. If the inner product of L of x with L of y is equal to the inner product of x with y for all x and y in V. So orthogonal transformations, or isometries. Now, there's a larger discussion to be had here. Like if you read, for example, Barrett O'Neill's elementary differential geometry book, he'll start by defining an isometry as being a transformation which just preserves the distance between points under the mapping. He doesn't even assume linearity. And he proves in there that, in fact, linearity is a necessary consequence of the assumption that distance between points is preserved under this isometry. But, you know, that's a little bit of a detour for us, so I'm just assuming linearity from the outset. There is a larger discussion to be had here where you could strip away the linearity and just consider possibly nonlinear isometry, prove linearity in fact follows. Well, it's not quite that. You could also have an affine transformation. If you look at a translation on a vector space, it will also preserve the distance between points. And so generally speaking, an isometry is some sort of composition of an orthogonal transformation and a translation. These together make what are called the group of rigid motions. For example, on our R3. Those are transformations on Euclidean space which preserve the shape of things. So like it'll, you know. Okay, so well, how does that go? There's another thing I have held back from you, which is the definition of the angle between two vectors. So if V and W are vectors in a real inner product space, and they're both non-zero, and as usual, we define the length of V to be the square root of the inner product with V, then the angle theta between V and W is implicitly defined excuse me, by the following. V W is equal to the length of V, length of W, cosine of theta. Now, this is also a definition. Now that definition, of course, begs a discussion, which is, why is it possible to define that cosine? Well, to see why that's the case, you should recall the Cauchy-Schwarz inequality, which stated that the absolute value of the inner product of V and W, all right? Cauchy-Schwarz said the absolute value of the inner product of V and W is less than or equal to, all right, the product of the magnitudes of V and the magnitudes of W, all right? So what's that mean? That means that if you look at the absolute value of the inner product of V and W divided by the length of V times the length of W, Well, that's less than or equal to 1, which means it's reasonable to suppose that this quotient can be identified with the cosine of some angle, right? And you could define angle in that way. For example, you check it out. I mean, and to be more specific, this theta is taken to be where theta is somewhere in 0 to pi, usually is what we do, all right? So if the vectors are orthogonal, what's the angle between them? 90. Right, because you'd have the inner product of V and W is 0. So you'd have 0 is equal to a product of non-zero things times the cosine of an angle between 0 and pi, so the answer's got to be pi over 2. So just like your usual geometric intuition, perpendicular things are 90 degrees separated. And you can just as well talk about that in inner product spaces, which is, I mean, you hope you appreciate, inner product space could be, I don't know, 10-dimensional or whatever. You might not be actually able to draw a picture of these vectors, but you can still calculate the angle between them, all right, in this way. So what's the significance of an isometry? The main observations is this: isometries preserve geometry, right? And what do I mean by that? Number one, excuse me, the length of x is equal to the length of L of x if L is an isometry. Well, let me be more specific. L an orthogonal transformation. I'm using orthogonal transformation and isometry as synonyms in here because I'm only considering linear isometries. Fine, there's also these translations which are isometries, and those are not orthogonal transformations. Perhaps I should just say orthogonal transformation. I'll get over it. All right, 2. The angle between V and W is equal to the angle between L of V and L of W. Why are these two claims true? It's almost immediate from the definition, right? So like the proof, what's the proof of this? Just what's the length of L of x squared? It's just what? L of x with L of x, right? Which is just what? So an isometry preserves the vector length. I keep saying isometry. I mean orthogonal transformation preserves vector length. And, well, the angle, right? So this would be what? This would be inverse cosine of like what? Of VW divided by the length of V, length of W. What would this be? Inverse cosine of what? L of V, L of W, right? Divided by the length of L of V, length of L of W. But what's that equal to? Definition of orthogonal transformation says that the inner product is preserved, right? So this gives you inverse cosine of VW. And downstairs by part 1, we also have length of V, length of W, which of course is the angle between V and W, right? So orthogonal transformations preserve angle and preserve length. Any questions? Now I've asked you guys, you have a homework question. What's your homework question? You're supposed to consider an orthogonal transformation from what? From like, say, Rn to Rn, right? Such that what? So this is an orthogonal transformation, and if L of x is equal to, say, Rx, what does that mean about the matrix R for this orthogonal transformation, right? I'm afraid I'm going to do your homework if I'm not careful, but maybe I can't avoid it. So check it out, right? We have L of x, L of y. Well, okay, we're in Rn. What's the inner product in Rn that what's our standard inner product? Just the dot product, right? Okay, so let's be more clear about this. This is, I'll make one more step like this, Rx, Ry. Okay, fine. Let me dispense with this. This is really what? This is Rx dot Ry, right? Which we can rewrite as a transpose. We can write it as a row column product, right? 1 by n times n by 1, which is 1 by 1. So we have Rx transpose times Ry, right? So, socks, shoes, this gives me X transpose, R transpose Ry. I don't feel too bad showing this to you. It's already in my notes. Yes. On the flip side, this is, of course, if you allow me this short manga style calculation, xy, which of course is equal to X transpose Y. Now you've got this is equal to that for all xy, right? I'll leave the details to you, but that implies that the identity matrix is equal to R transpose R. Okay? That condition is that's the defining condition for R to be a so-called orthogonal matrix. So the orthogonal matrix is the matrix of an orthogonal transformation. Kind of good terminology, yeah. All right, so this defines the following. O(n) is equal to R in n by n matrices such that R transpose R is equal to I. This is the set, or if you like, the group of orthogonal matrices. It's a group in the sense of abstract algebra. You can prove the product of orthogonal matrices is once more orthogonal. You can prove that the inverse of an orthogonal matrix is orthogonal. So that forms a group. The identity matrix is also in there. Any questions? No so far? Okay. This implication is not hard to get. Just take x and y to be like EI and EJ. That will pick off the ijth component of this, and the ijth component of this will just be the Kronecker delta, right? Just set x equal to EI and y equal to EJ. It should immediately follow that, is the case. There's also an identity. This is a lemma I have earlier in the notes, that if you can prove this identity for all x and y, it then implies that the matrix here and the matrix here are equal. The matrix here takes a little imagination. This is the same as X transpose I times y. So if you have this for all x and y, there is a cancellation. You're allowed to get this is equal to that. Okay, that's all I did. All right. So this is the orthogonal, or the group of orthogonal matrices. There's also special orthogonal matrices. Now, if you look at the determinant, what happens if we look at the determinant of such matrices? What do you got? The determinant of R transpose R is equal to what? It's equal to 1, right? But it's also equal to the determinant of R times the determinant of R transpose, right? Which is, by the way, the determinant of R squared, which, yes, is equal to 1. But this is a real number. So we're looking for the determinant's a real number, right? The only solutions that are allowed to this are what? Yeah, plus or minus 1. So it turns out the plus 1 solutions correspond to what we know as rotations. All right? The minus 1 determinants, the orthogonal matrices with determinant minus 1 correspond to, like, sometimes that are called rotor reflections, or they're reflections paired with rotations, or just, it's a reflection. There's some kind of inversion going on. All right. That's about it. Now, there are beautiful structural theorems that are given in Curtis that pretty much pin down what's possible. And I've asked you a homework problem or two, which basically has you explore particular cases of these rather general theorems he gives you. So in section 30, he defines the notion of an irreducible subspace. An irreducible subspace is one which can't be broken down further. All right, it's like it can't be. It's like fundamental. All right, and basically what he argues here is that well, theorem 30.2 says if V is a vector space over an algebraically closed field, then every irreducible invariant subspace W relative to T has dimension 1. If you're over the reals, then every irreducible invariant subspace has dimension 1 or 2. All right? And then he proves that if you have an orthogonal transformation, it has to have a very special structure with respect to, if you restrict an orthogonal transformation to an irreducible subspace, it has a very particular structure. Eventually he comes to this following theorem, which is like sort of all-encompassing. I'll just put it down here for us. Theorem 30.5. I've really just asked you to explore a subcase of this in the homework. Let T be an orthogonal transformation of a real vector space V with an inner product T, V to V, T, orthogonal. So he's a little bit greedier. He's doing it for an abstract inner product space. Fine. He says, well, then there exists a basis for which, let's be more specific. I'm changing it a little bit, beta, for which the matrix of T with respect to this basis looks like the following. He's got ones, and then minus ones, so many minus ones, and then he's got blocks. And the blocks we know, they're cosine theta 1, minus sine theta 1, sine theta 1, cosine theta, sorry I'm writing so small, right? I'll make the next one bigger. Cosine theta 1, minus sine theta 2 rather. Sine theta 2, sine theta 2, cosine theta 2, and so forth. And he has, I think, a somewhat accessible proof of this in section 30. I'm not going to do it because you guys have suffered enough from me almost proving things. But that's basically what an orthogonal transformation looks like in general. You can find a basis that makes it just basically, you're just either fixing these, so like these first so many coordinate vectors you're just fixing. They're like axis vectors. They don't move, all right? And then these, you're like flipping, those are inversions. You're flipping over the axis for those ones. And then these guys, well, those are rotations around certain planes. So generally an orthogonal transformation is some sort of combination of just fixing certain directions, flipping other ones over, and then rotating in planes. In 3 dimensions, all you can have is like one of these guys and one of those guys, right? And if your determinant's 1, if you're an SO3 atom, if you're an SO3, then all you can have is one of these guys and one of those guys, and that's it. So every 3 by 3 SO3 matrix can be written as a rotation around some axis. And I think you've just about found that now, right? Proving it seems like it should be easier than it is. I've wasted hours on that myself. Yeah. When you see my solution, you're going to be like, that wasn't hard. It shouldn't have taken so long. Man, that was my feeling after I wrote it down anyway. But this is the general theorem. Okay, so yeah, that's an orthogonal transformation. All right, so let's get next topic here, changing gears a bit. Not too much, though, actually. So what's a quadratic form? I'm going to be less abstract than the textbook. Now, in Curtis, this material is, let's see here. Oh man, where'd it go? I guess it's section 31, give or take. It's his principal axis theorem. And he describes in there how to define a quadratic form for a real inner product space. All right. And I'm not going to try to do that right now because I think it's more natural to do after we've had another discussion, which we have not yet had. And so what I'm going to do today is I'm going to give you a more pragmatic definition of a quadratic form. And I'm just going to define the quadratic form on R2 or R3 or Rn, all right? Because that's all I'm really interested in. That's all of our examples. They're all like that, okay? So let's focus on quadratic forms on Rn. Okay, so what you're looking at is something like this. Q is a mapping from Rn to R. All right? And basically, just to cut through the static, the deal is this. You can write matrix, in fact, a unique matrix A, which is symmetric. And Q of x is just equal to x transpose AX. So this is our definition. It's our working definition. It's a good definition, though. All right, so this is a quadratic form. What does that look like? Let me give you some examples. Here, for R2, I could have like xy equal to x squared plus, say, 2xy plus 3y squared. For 3 dimensions, I could have q of xyz equal to like, I don't know, x squared minus y squared plus, I don't know, pi z squared. So you see why they're called quadratic forms, right? It's because they're basically homogeneous polynomials of degree 2. They're quadratic. Now, let me go back to my, what is the matrix of these forms? So it's going to be 2 by 2 in this case. Over here, it's going to be 3 by 3. Right. So then what? Well, I'll just do it. 1, 1, 1, 3. You can check me on it. If you multiply that back out, you produce an xy and another xy. You produce 2 of them. They add together to give you 2xy. This one is kind of more boring. It's 1, minus 1, and pi. And then zeros elsewhere, right? Let me do another one. Suppose we're just equal to like xz. What would that be equal to? Now, you see, if you were ignoring my insistence that we use a symmetric matrix, right? In principle, you could just write like this, right? Because if you multiply this times that, it gives you the matrix, it gives you the column vector what? Z, 0, 0. And then you multiply it by this, and you get what? You get xz, right? So this, in terms of formulas, this is legitimate. It's not legitimate in the sense that that is not the matrix of the form Q, right? So what do I have to do to make it symmetric, okay? So instead of putting a 1 just there, I put a half and a half. And there you go. This is what we call the matrix of Q, okay? So far, so good? Why do we care about quadratic forms? Like, how about this? Is there a question? How about this? What if I have x squared plus y squared equals to 1? If I have x squared minus y squared equals to 1, you guys can tell me immediately what these are, right? Circle, right? This is what? It's a hyperbola. Which way it opens what? If I put x equal to 0, I got no solutions. This is a sideways opening hyperbola, right? But what if I have xy equals to 1? That's a quadratic form. We're looking, so these are level curves that are constructed from quadratic forms, right? And I propose to you that when you have something like this, it's not maybe immediately obvious what that is. In fact, what you see it is, I mean, you know that's y equals 1 over x, right? And given this discussion in this context, and well, if you've had calculus with me before, you might have heard me say that it's a hyperbola rotated 45 degrees. What's the significance of, what does that mean? I mean, that means that there's some kind of rotated coordinate system, right? Where this equation looks like what? Maybe some constants out here, I don't know. I'm not sure exactly, but it's, right, there's some coordinate system which we could find that would make it look like that, right? Because then, you know, this would be y bar perhaps, this would be the x bar coordinate system, right? How do you find these hidden coordinate systems that reveal the true nature of a quadratic form? That's the question. So you guys you're comfortable with at least what a quadratic form is? If it's already diagonalized, we hardly need the theory, right? Like this is really easy to understand. How does this behave? Oh, actually, how do we, before I spill the beans and tell you the main theorem, there's one other fun fact I should share with you, is quadratic forms are fixed by, say, vectors of length equal to 1. Check this out. So if I have q of x, right? It's x transpose ax, right? I can rewrite that, right, as the length of x times x hat transpose a, the length of x times x hat, like so, for x not equal to 0, fair enough, all right? So if I'm at a non-zero point, I can express the vector as its magnitude times its direction, its unit vector as we defined the other day, right? And you can pull out by properties of usual properties, well, what's that? That's the magnitude of x squared, right? X hat transpose a x hat. Notice that x hat, the length of x hat by construction, you know, is 1. And so x hat transpose a x hat is equal to q of x hat, right? That is in fact the value of the quadratic form on the so-called unit sphere, the collection of points distance 1 from the origin. What this little calculation shows you, right, is that the behavior of the quadratic form is completely fixed by what happens right here, right? Whatever the values are on the quadratic form on the unit sphere, those completely pin down the way it behaves all the way out to infinity and back to 0, right? So that's, I think, something important to notice about quadratic forms. I will use that as part of my thinking here in just a second. All right, so what's the real spectral theorem? It's the following. If A is equal to A transpose, in other words, if A is a symmetric matrix, then there exists an orthonormal, that's with respect to dot product, okay? Get this, eigenbasis. And all the eigenvalues of A are real. So quadratic forms are built from such a matrix, right? Now let me unpack what I'm saying here. That means that there exists what? Beta, V1, V2, Vn, such that what? A Vj is equal to lambda j Vj. For j equals to 1, 2, da, 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 n. These could be repeated, but they're all real, right? But greedier still, ever so much more greedy than this, they are orthonormal. That's awesome, because that means orthonormal. What's that mean? That means that Vi dot Vj is equal to Kronecker delta Ij. And what that implies then is that the matrix of beta transpose times the matrix of beta is equal to the identity matrix. So what I'm telling you, all right, and you can prove this, is that an orthonormal basis produces an orthogonal matrix. The wording doesn't quite match up, okay? Sorry. You do need orthonormality to get orthogonality of the matrix, like this. Right. And so, hence, you know, the usual result is what? P inverse AP is equal to the diagonal, right? What does that become? In this context, that just becomes the basis matrix transpose times A times the basis matrix again is equal to the lambdas. There's no inversion, there's just transposition. Awesome. I like not inverting things, don't you? What if I had used a different coordinate system? See, if you go back to here, what if instead of saying, what if I had used, like, with respect to the beta coordinates to set up the formula? How would that have been different? This is what? This is beta inverse times x, right? But if we're using an orthonormal coordinate system, that's just beta transpose times x. So if I want to rewrite this in terms of that guy, what do I do? Takes a little imagination here, guys, but that's X transpose beta by sock shoes, right? So all you do is just fit in some copies of what you want, right? What am I doing? I did nothing more than insert 2 copies of the identity matrix, right? This is the identity, that's the identity. Why did I do that? Very simple. This, you see, is that. This is that, right? So what I have here is I have the coordinate vector with the eigen coordinates, all right, transposed. And what's in the middle? What's this beta transpose A beta? Well, with respect to the basis given to us by the real spectral theorem, that's nothing more than a diagonal matrix with eigenvalues down the diagonal. If you call, so what you can rewrite this formula, you'll excuse me, you can rewrite this more explicitly. This is just lambda 1 x bar 1 squared plus lambda 2 x bar 2 squared plus dot 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 plus lambda n x bar n squared. So an pretty much immediate corollary of the real spectral theorem is the fact that any quadratic form can be, let's say, diagonalized, in the sense that you can remove the cross terms and you can rewrite the formula just as an eigenvalue weighted sum of squares of the eigencoordinates. These are eigencoordinates, the x1 bar, x bar 2. It's what I had pictured over here. What are the minimum and maximum values the quadratic form takes on the unit sphere? So if we have the length of Vj is equal to 1, right? Thus, Vj is equal to Vj hat, okay? So if you look at that, you know, Q of Vj is what? It's Vj, A, Vj, which is what? Transpose. It's Vj transpose, lambda j, Vj. It's just equal to lambda j. So the unit eigenvectors, right? The values which they take on the unit sphere are simply the eigenvalues of the quadratic form. So you make a list of the eigenvalues of the quadratic form, and that shows you the biggest and the smallest that the quadratic form can be on the sphere, and consequently it tells you how the quadratic form behaves everywhere else because of this little identity. So let me pick on a specific example here. This guy. Is this, if you set this equal to a constant, right? A positive constant, is it an ellipse? Is it a hyperbola? Is it a parabola? That's the other possibility, right? Well, I guess lines. So what you do is you just look at the matrix, 1, 1, 1, 3. That's my matrix, right? I calculate the determinant of A minus lambda I. What's that give me? Uh-oh. I just made this up. It could be ugly. That's lambda minus 1 times lambda minus 3 minus 1. Oh. I'm not optimistic about this. Lambda squared minus 4 lambda plus 2? Plus 2. Complete the square. I should be more optimistic, though, because this is a symmetric matrix, which means it has real eigenvalues, if I trust the theorem. right? So this is lambda minus 2 squared, and that does what? I have to subtract what? Subtract 2. So I've got lambda minus 2 plus the square root of 2, lambda minus 2 minus the square root of 2. It ain't pretty, but you know what? If you're willing to trust the general derivation that I just did for you over here, right here, you know that there exists an eigenbasis, and the formula, once we find the eigenvectors, is simply the following. It is 2 minus the square root of 2 x bar squared plus 2 minus, rather plus the square root of 2. Yeah. Y bar squared. And then you can ask the question, so what is, if I set this equal to a constant, what is it? Is it an ellipse? Is it a hyperbola? What is it? The coefficients are both what? Yeah, 2 minus root 2, 2 plus root 2. They're both positive, right? So both of the eigenvalues are positive. If you look at this equal to a constant, what you're looking at is an ellipse. So basically, if I give you an orthogonal matrix, a symmetric matrix, right? Something that's equal to its own transpose, and I tell you to find eigenvalues and eigenvectors, you should be like, thank you, sir, may I please have another of these? Because that means it's a very nice example. Not only can you find all of the eigenvalues, you don't have complex eigenvalues, they're all real eigenvalues, and not just that, you can select the eigenvectors to be orthonormal, which means the calculations are very pretty. It's a huge result. Let's see here. One other application of this, which you might find interesting. I know you can. If you look at functions, I'll just stick to 2 variables for a second here, okay? So if you look at a function 2 variables, you can express it as f of ab plus the gradient of f at the point ab dotted with x minus a, y minus b, and then plus a quadratic form in x minus a and y minus b. In particular, and then plus dot dot dot. This is the multivariate Taylor expansion. A critical point is one for which what? You have the gradient, which is, by the way, partial f, partial x, partial f, partial y, right? So if you have a critical point, you have this is equal to 0, right? That's a critical point. Now the quadratic, the Q, in more detail, the matrix of Q is the following. Fine. Q of x minus a, y minus b is 1/2 fxx at the point a comma b, x minus a squared plus fxy at a comma b, x minus a times y minus b plus 1/2 fyy a comma b, y minus b squared. You can rewrite this, of course. This is a quadratic form in the sense that if you just look at it, you've got, this vector x minus a comma y minus b, right, times this fxx a comma b, and you can pull the 2 out, right? Let's just pull the half out. I'm going to pull a half out here because it's not important. Pull the half out. And then you have fxx, you've got fxy, What's the relation between fxy and fyx? They're equal, right? So this is the matrix of Q, all right? It's called the Hessian. So it's a 2 by 2 matrix. What's the relation between the eigenvalues of a 2 by 2 matrix and the determinant and the trace? Like, how's it go? The determinant of Q should be what? It should be the product of the eigenvalues, right? And the trace of Q should be what? Okay, what's the product? So the determinant of Q can also be written as what? It's fxx. I'm going to drop the AB dependence if you guys don't mind. It's fxx, fyy, minus fxy. Hold on a second. If you've had calculus 3, sorry if you haven't, that should be familiar. What is that? That's the big D, right? In a lot of books, sometimes that's called the Hessian. That's the thing, if it's negative or positive, then you get the second derivative test, remember? So how can you have the product of two real eigenvalues be negative? It would be what? If one is positive and one is negative, right? If that's the case, then what does this thing look like? Near a critical point, right? Near a critical point, this thing looks like the following. The value at AB plus lambda 1 times, let's say, change in x bar squared, plus lambda 2 change in y bar squared, where those are the changes in the eigencoordinates close to the point of the expansion, close to the critical point. So if these are one positive, one negative, that means there's one direction you're increasing and there's another direction you're decreasing. It's a saddle point. That's why if d is less than 0, you have a saddle point, because it looks locally, if you could zoom in on it like a hyperboloid or whatever, it's saddle shaped. On the other hand, what happens? If these are both positive, right, then d is positive, and that would mean what? It looks like a constant plus a sum of squares. That would be like a paraboloid that opens up in 3 dimensions if you're graphing it. If you have d is positive and these are both negative, right, then it's like a paraboloid that opens down. And that's a second derivative test. So if you understand eigenvalues of the Hessian, you can see where that's coming from. And also, you're not limited to 2 variables. You understand to test the minimum or maximum of a function of more variables, all you have to do is look at the quadratic piece, right? If it's a critical point, calculate its spectrum. By the way, the spectrum is the list of eigenvalues put in order. So if you understand the eigenvalues of the Hessian, then you can determine whether the function has a minimum or maximum or a saddle or whatever, whether you're in 2 dimensions or 30. It's just a little more calculation. But this is how you do it. Now, so many chords. Where's the one I want? No, that's not it. Oh, here it is. Too much technology. Technology dehumanizes. Let's see here. All right. So in the, come on, wake up. Stop your circle wheel of nonsense. Wake up. You can do it. All right, where are we? There it is. So what I've been trying to do to you, for you, is to explain to you just this bit about quadratic forms and their matrices. I have many beautiful pictures, and some are like obvious, like, okay, if you've got a quadratic form with no cross terms, then you don't really need software to figure out if you've got x squared minus y squared, it's a hyperboloid. Or if you've got 3x squared, it's a paraboloid. It's just a trough, parabolic trough. Or if you've got x squared plus 2y squared plus 3z squared, if you look at the family of family of set that's equal to a constant, you get ellipsoids, But what's interesting is when you start looking at terms that have, so here's actually explicit details. I start with 2x squared plus 2xy plus y squared, and we discover with respect to the eigencoordinates, it just looks like this. So that's the real, that reveals the true nature of the quadratic form. And you can see the graphical significance of this if you're really good at looking at pictures. And here's another one. So the point of these is you choose eigencoordinates and it makes it simple. Here's a rotated ellipse. See, the original equation was, somewhat complicated. Up here, see that? 6 minus 2, 0, 2 minus 2, 6, 0, 5. And when you do the rotated coordinate system, you just get a diagonal matrix 4, 8, 5. And so I hope I've told you enough today that you can understand what it is. Oh, actually derive you could skip over this if you don't care about the multivariate Taylor expansion.